Sheridan College's Industrial Process Control. This video is Lab 1, Point Level Control. This lab will demonstrate a simple system to control the level of water in a tank by using a low-level and high-level switch arrangement. The holding tank card has the following components: two two-way hand valves, a cluster of hose termination points on top of the tank, the holding tank itself with its lid, a three-way hand valve to redirect the water, a level controller, motor, and pump assembly. The receiver column assembly has the receiver column itself, two proximity switches identified as LS1A and LS1B. The two switches will identify the upper range value and lower range value, a PLC control element, and hose connections to the holding tank and pump assembly. The lab begins with the receiver column empty. LS1A and LS1B are not made, so the control element PLC turns on the pump. Water is then pumped into the receiver until LS1B is made, and then the pump is stopped. When both LS1A and LS1B are made, the upper range value has been reached, and the control element PLC stops the pump. This allows gravity to drain the receiver of its water. When the level of the water is lower than LS1A, both the switches are off, and again, this triggers the control element to restart the pump. This system will continue to fill the receiver tank between the 2 points. The wiring required only some simple connections from the true proximity switches to the PLC control element, and then from the PLC control element to the level controller and pump motor combination unit. The piping required was already on the holding tank and pump unit. The supply line was fed into the bottom of the receiver column, and the return line came from the receiver column back to the holding tank.
Okay, so what we have here, Lab 1, point level measurement. It's an on-off control. Point level because we're really only concerned with the level at any particular point. In fact, in these 2 points, we have set up with these capacitance proximity detection switches. Okay, so it's an on-off control because the corrective action is either there or not there. The pump is being turned on, and then it shuts off once it gets up to the upper range value. There is no in-between states. So this type of detection of level is called a direct level measurement. It's because these capacitance switches actually are reading the water itself. We're not using some other aspect of this process and trying to determine the level by calculation. Okay, so let's look at the parts of this system itself. What we actually have are 2 primary elements. They sense the condition of the process variable. There is no transmitter in this process. These feed directly into our control, and we don't use a signal from a transmitter.
Capacitive proximity switches. Capacitive proximity switches work on electrostatic energy and capacitance rather than electromagnetic energy and inductance. As the object passes the electrostatic field, the capacitance of the circuit changes. This alters the stability of the underlying tank circuit, which begins to oscillate and generates a signal when the trigger value is exceeded. Capacitance proximity switches can sense an object through a medium such as glass, and the object does not have to be metallic.
What we feed from our control here out to our pump is actually a 4 to 20 milliamp signal, which is a standard current instrument signal. It has a span of 16, and it has an offset of 4. Okay, so we have the primary sensing element, PLC, which is overkill in this box. And then what we have is a motor pump combination, and that's actually our final element. That's what's doing the work. Now, we have a process variable, and the process variable is actually the water level in this particular tank. That's what we're controlling, water level in this tank. The manipulated variable is what we're manipulating in order to fill this tank back up and once it's drained out. Now, our manipulated variable is actually 2 things. One of them is the electricity we're using. We're turning on and off electricity by relays to turn the pump on and off. The other one is water. By turning the pump on, we actually feed more water into our process. So you can actually argue both ways. So we have electricity as the manipulated variable and water from the tank as a manipulated variable. Okay, so what we see here is we actually have a deadband to this process. Deadband actually in this case is necessary. Now, if you notice, it comes up to about 12 inches and it shuts off, and then it drains out. It's down to about 5 inches. And what we have is a deadband that is between those 2 numbers. Now, our upper range value being 12, our lower range value being 5. Now, if we look at what happens here, the water level fills up, the pump shuts off, but the water level drops. So what we actually have here is some dead time. The process variable has changed, but there is no action by the controller. Now, if you'll notice, if I count out 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009, about 9 seconds dead time. I'm going to change the process. I'm actually going to put in a bit of a disturbance, and this disturbance is to restrict the amount of flow out of the tank. So what I do is I close one of the valves, and let's see if that has an effect on our dead time. 1001, 1002, 1003, 1004, 1005, 1006, 2007, 2008, 2009, 2010, 2011, 2012, 2013, 2014, 2015. About 15 seconds. What we have here is a 6-second difference in dead time. Now, the dead time can change depending on the load on the system, but the dead band is something that has been adjusted in this system. Now, in this type of control, since we have water being detected by these capacitance detectors, the only way we can actually change the liquid level, or in fact the set point, is by moving these detectors. Now, what I'm going to do is I'm just going to shift one up a little bit. So what I'm changing here is the deadband. Move this up. And I'm going to open up the valve so I'm not worrying about so much dead time. A little out of adjustment. There we go. Okay, so what I've done is I've changed my deadband. And in fact, there we are. Okay. All right, now, deadband in some cases can be detrimental to your process because what you have is too much of a lag. But what I'm going to do is I'm going to reduce the deadband to nearly 0. What I want you to notice is what you hear from the primary, from the final element. So if I move these sensors very close to each other, what you hear now, because I've reduced that deadband, is you hear this pump cycling on and off. Now, for a small motor like this isn't a problem. But if this happened to be a larger motor, having that turn on and off, that inrush that you would get to the motor, could cause it a lot of wear and tear. Also too, if this was a valve, the valve would be cycling open and closed a lot. So having that deadband in there actually saves the equipment, and we don't need to have it at exactly any point in here. We're just worried that it's going to be between two points of our range.